Good morning. Welcome to another session of distributed generation and smart grids. In this session, we will discuss about wind energy conversion systems. So before we start the session, let us see a quote by Dr. APJ Abdul Kalam. You were born with wings, don't crawl. Learn to use them to fly and fly. So we are in module 2 and we had already discussed CHP systems and PV systems earlier, and today we are going to discuss wind energy conversion systems, or abbreviated WECS. I'm sure you might have seen a wind turbine, or at least pictures of a wind turbine. So a wind turbine looks like this as shown in figure. There are rotor blades, maybe 3 rotor blades in most wind turbines. The wind falling on the rotor blades keeps the rotor blade rotating. Then another part of the wind turbine is called the nacelle, inside which the gearbox and the generator are housed. The output of the generator flows down the tower through cables, and then it is stepped up to proper voltage by using transformers, and then it is transmitted to the nearest substation. The wind turbine is coupled to the generator through a gearbox. Why we need a gearbox, we will see later. So usually induction generators are used in wind energy conversion systems which produce 3-phase AC. So wind turbine captures the kinetic energy of wind flowing through the rotor blades and transfers the energy to the induction generator side through the gearbox. The output voltage and frequency is maintained within specified ranges by using supervisory metering, control and protection techniques. So windmills are available with capacities of 10 megawatt. Now you can see this news article dated September 2018. So MHI Vestas launches a 10 megawatt wind turbine. The rotor diameter is 164 meters, 80 meter blades. Each blade weighs around 35 tons, and the tip height is 187 meters. So a single turbine can power approximately 5,977 German homes. And the advantage is the reduced operational and maintenance cost. And this turbine, a 10 megawatt turbine, will be commercially available by 2021. Here you can see different parts of a wind turbine. So the main part is this part, which is called the rotor, and this part, which is called the nacelle. Here you can see the rotor blades. This is also a rotor blade. So a third blade also is there. This is the third blade. So the wind direction is perpendicular to the rotor blades, and this keeps the rotor blades rotating. And when the rotor blades rotates, this shaft This is called a low speed shaft rotating. The low speed shaft is connected to a gear mechanism. So their gear mechanism converts low speed to high speed. So this side the speed will be high, and this high speed part is connected to a induction generator which produces 3-phase AC. Okay, so there is a yaw drive and yaw motor here. This yaw motor is essential to make the direction of the rotor perpendicular to the wind direction. So the wind direction might slightly change. The yaw motor will adjust the rotor in such a way that it always faces the wind. The swivel beading and the swivel wires are essential to take out the generated electricity from a rotating part to a stationary part, and the cable goes down the tower to the transformer. Here you can see a wind vane and an anemometer to measure the wind speeds, and the controller measures the wind speed, and if the wind speeds are very low, then this rotor cannot work, and also if the wind speeds are very high, then we need to have a braking, otherwise the entire system will collapse. So this controller is essential to stop the wind turbine when the wind speeds are very low or very high. So usually the wind speed should be more than about 6 meters per second. Below 2 meters per second, the turbine cannot work. You can also see here, by controlling the angle of the rotor blades, and this angle is called the pitch angle, we will be able to maximize the torque produced. Okay, so that's also another control system involved in a wind turbine. This is the equation of the power developed. P is equal to half Cp rho V cube A. P is the power output in watts, Cp is the power coefficient, A is the rho is the air density, V is the wind velocity, and A is the swept area of rotor blades. Cp gives a measure of the amount of energy extracted by the turbine rotor. Its value varies with rotor design and the tip speed ratio. Tip speed ratio, or TSR, is the relative speed of the rotor and the width, and it should be less than 0.4. The torque output varies due to fluctuations in wind speed caused by tower shadow. So tower shadow means the rotor blade comes in front of the tower. So at that time the torque cannot be generated by that particular rotor blade. So wind shear is also important, and turbulence causing dynamic perturbation in the output power. So depending on controllability, the wind turbine operating systems are classified into constant speed wind turbine and variable speed wind turbine. So a constant speed wind turbine is characterized by power variation and voltage flicker, whereas a variable speed wind turbine provides smoother output power and more stable bus voltage with less losses. Here in the picture you can see a constant speed wind turbine. The wind force acting perpendicular on the wind turbine rotates the wind turbine, and the output of the wind turbine connected to a low speed shaft goes to a gearbox where the speed is changed to high speed, and then it is connected to a rotor producing AC, and this is connected to the grid. Now the constant speed wind turbine, here since we have a gearbox, we can predetermine the generator speed using a gearbox. The control schemes are aimed at maximizing either energy capture by controlling the rotor torque or the power output at high winds by regulating the pitch angle. Pitch control is the technology used to operate and control the angle of the blades in a wind turbine. The system in general is made up of electrical motors and gears, or hydraulic cylinders and a power supply system. According to the control strategy, constant speed wind turbines are again subdivided into stall regulated turbines and pitch regulated turbines. So you can again use a control strategy either by changing the pitch or changing the stall angle. Here you can see a turbine blade is shown. Two forces act on a turbine blade. One is called a lift force and another is called a drag force. So the lift force will be high at alpha is equal to low, and the lift force will almost become zero when alpha is high, and we call this condition as stall. So our basic idea is to make the drag forces as small as possible and maximize the lift forces. The advantage of constant speed wind turbines are they are very simple, very robust construction, and they are electrically efficient. And they are highly reliable because there are only fewer parts. And no current harmonics are generated, and there is no frequency conversion. The capital cost is low as compared to a variable speed wind turbine. The disadvantages are they are aerodynamically less efficient and prone to mechanical stress and are more noisy. Here you can see a variable speed wind turbine. You can see the turbine blades connected to a gearbox mechanism and induction generator, and this is the output of the induction generator. The speed is measured, and the speed, there is a relation between speed and power, and this is used as a feedback mechanism to adjust the pitch angle. This is the pitch angle mechanism which will adjust the pitch angle of the rotor to maximize the torque. The control strategies usually employed in variable speed wind turbines are: number 1, power optimization strategy, and number 2, power limitation strategy. So the power optimization strategy is employed when the wind turbine is below the rated value. So this strategy optimizes the energy capture by maintaining a constant speed corresponding to the optimum TSR. And in power limitation strategy, it limits the output power to the rated value by changing the blade pitch to reduce the aerodynamic efficiency. The advantages of variable speed wind turbine: high energy capture capacity and are subjected to less mechanical stress. They are more aerodynamically efficient and have low transient torque. No mechanical damping systems are required, as the electrical system can effectively provide the damping. They do not suffer from synchronization problems or voltage sags due to stiff electrical controls. The disadvantages are lower electrical efficiency and more expensive and require complex control strategies. This is the world's third largest wind farm, or India's largest wind farm, situated in Tamil Nadu, the Muppandal wind farm. There are about 3,000 turbines set up on the farm, which produces 1,500 megawatt of clean energy. So these are some of the references. Please go through them in depth, and thank you very much. With this, we end this session on wind turbines or wind energy conversion systems. We will see again with another session soon. Thank you very much.